Hello everyone, my name is Riquelme and I'm a PhD candidate from the IFT in Madrid, and I want to present to you today in this conference about primordial non-Gaussianities from the angular clustering and the prospect for the dark energy survey. So before starting, let me introduce you a little bit about the project in general within the dark energy survey collaborations. So first of all, a first disclaimer is that the following results are preliminary, but they are expected to be really soon, so keep on tuned. And the second point is that essentially the results for primordial non-Gaussianity will be presented in a series of two papers. The first one containing mostly methods and optimization for primordial non-Gaussianities using angular correlation functions, which is the topic of this presentation. And the second paper containing the actual constraints for the dark energy survey GR3 results. So it's a pleasure for me to be speaking on behalf of this really amazing team, which I'm pointing out here. And with that, let me start first defining to you what is primordial non-Gaussianity. So primordial non-Gaussianity appears essentially in the context of cosmic inflation, and it's relatively well known that cosmic inflation is so far the best model that we have in order to describe how the initial conditions were produced. And essentially cosmic inflation predicts a way of computing correlation functions of these curvature perturbations, where these curvature perturbations serve as initial seeds for the creation of structures. So in principle, for example, if you have these curvature perturbations, you can compute two correlation functions of them and obtain, for example, the power spectrum. And with that power spectrum, you can use that as an initial condition for the rest. For example, in the temperature fluctuations of the cosmic microwave background, you can obtain the temperature fluctuations power spectrum. Or if you do it now in the late universe, you can obtain the matter power spectrum, for example. One important information that this tells us, and that has been constrained before, is that cosmic inflation predicts a nearly close to Gaussian distribution for these fluctuations, but you can still try to explore more by computing higher order point correlation functions, such as, for example, the 3-point correlation function, which is called the bias spectrum. And this bias spectrum can be a window to disentangle between the different models of inflation. This bias spectrum is essentially parameterized by this really important parameter, which is called the FNL parameter. So this parameter has been constrained before using CMB experiments. So these curvature perturbations, as I said, will affect the temperature fluctuations in an early radiation era. And with that, you can compute, for example, 3-point correlation function of these temperature fluctuations. So you can compute essentially triangular configurations from these temperature fluctuations, and with that, you can constrain this FNL parameter. So the question now is that, can we constrain this FNL parameter using large-scale structure in the universe, such as galaxies or other bias tracers of matter? And the quick answer is yes, we could, but maybe it's not the best idea, because you can have, for example, that the gravitational evolution from the creation of this structure could also induce non-Gaussianity to these structures, and at the end will be really difficult to disentangle between non-Gaussianity coming from a primordial origin or non-Gaussianity due to the gravitational evolution. So the question is, can we actually put constraints on this FNL parameter, maybe using some other way? The quick answer is yes. We can use something called scale-dependent bias, and the idea is the following. So you have the curvature perturbations affecting a matter background, and this matter background will essentially generate dark matter over densities. And in order to relate these dark matter over densities to galaxies over densities, for example, you need to introduce some bias parameter. This is called, in this case, the linear bias. And since now that you have primordial non-Gaussianity, essentially the effects that primordial non-Gaussianity has is that it modifies the way how the Newtonian potential behaves, modifying, for example, the Newtonian potential in this way, with now as a function of this FNL parameter. So this essentially will modify the way how the Poisson equation looks, and at the end introducing some modifications to this linear bias by now this FNL parameter, and also introducing this m of k function. this m of k function has now a really important behavior, encoded essentially in this 1 over k squared, which implies that we will have an enhancement effect at really large scales. So what is the effect of this scale-dependent bias in the summary statistical of a large-scale structure? In principle, in the left one, you have the effect that it has in the power spectrum. So where you see now this scale-dependent bias is a function of FNL, and in here you are seeing the galaxy power spectrum. For example, for the red line, you have an FNL value of 100, and in the blue line, you have an FNL value of minus 100. So then this similar effect can also be seen in the tube correlation function, which is the Fourier counterpart of the power spectrum, and in that you can also see that you have an enhancement at large scales due to this FNL parameter, where you have also this red line, which is almost a 90 FNL 90. So now that we know the effect that the FNL parameter could have, for example, in the power spectrum or in the tube correlation function, we can see some results of constraining FNL using large-scale structure and evolution through the years. So we have, for example, in this really nice summarized plot created by Eva Maria Müller for the latest EVOS results. You have in blue the constraints coming from large-scale structure, and you have in orange the constraints coming from CMB. And there are essentially three main points that you can obtain from here. The first one is that CMB experiment had already reached the cosmic invariance limit in order to constrain this FNL parameter. So these are the tightest constraints that you can obtain using cosmic macro background experiments. Another point is that mostly all of these results coming from large-scale structure are using spectroscopic surveys. So it's really interesting, and it is expected that for photometric surveys to play a big role in breaking this FNL, this sigma FNL order 1 barrier. And with that, let me introduce you to the main photometric survey of our interest, which is the dark energy survey. And the dark energy survey is a photometric survey located in Chile, covering an area of almost 5,000 degrees, and essentially has a galaxy sample divided in 5 redshift beams due to these uncertainties on that you have and determine the redshift position of objects. And it's covering also a redshift range from 0.6 up to 1.2. And this is essentially based on the BAO galaxy sample. So in here you can see the angular distribution of the dark energy survey, and in the right plot you can see the N of C distribution, so number density distribution according to the redshift beams. So now that we have described the survey and where the data will be coming from, let me describe you the theory that we will be using to constrain this FNL. And from the previous cases, there have been using power spectrum or tube correlation function, and instead we are going to present a new way of using the angular correlation function, which is essentially a tube correlation function but projected in a two-dimensional projection of the tube correlation function, which essentially includes the information of the N of C distributions. So here in this plot you can see that the angular correlation function, it is also affected by this FNL parameter, as you can see, for example, in the orange lines where you have a value of FNL 100, you have in blue line the value of FNL 0, and in the green one you have a value of FNL minus 100. Now that we had described the theory before, let me describe now the simulations that we will be using in order to compute and obtain the prospects. So we will essentially have two kinds of simulations. So we will have first the ICE-COLAMOX, which are simulations that resemble the dark energy survey angular distribution and redshift error distribution. And we also be having simulations that has primordial non-Gaussianity as initial conditions, and this will be called the Goliath PNG mocks. And they have initial conditions of FNL of minus 100 and 100. Now that we have the simulations, let me describe one last ingredient before going to the actual prospects, and this ingredient is the integral constraint, which turned out to be really important in order to constrain the FNL. So what is the idea behind it? Let me start with the definition of the estimator from the angular correlation function, where the angular correlation function is essentially defined as an excess probability from a mean density of an homogeneous background. And for the particular case of Windows surveys, the number of galaxies is estimated by the mean density of the survey, which essentially implies some particular constraint that the angular correlation function from the observational aspect needs to accomplish, which is essentially an integration over the whole Windows survey of the angular correlation function needs to go to 0. This essentially led us with the integral constraint condition, which in here we're including the random correlations, which is a way to include the integration over a Windows surface. Why is this important for the particular case of FNL and the angular correlation function? Essentially because an angular correlation function with primordial non-Gaussianity will have a large-scale clustering enhancement that will depend on this FNL value. And in order to control this, you need to impose this integral constraint condition that I mentioned before to have the theory and the angular correlation estimator in the same footing. So you need to correct your theory now with this function of FNL, and this function will be essentially obtained by imposing the previous integral constraint condition. What is the effect of this integral constraint? We can see that clearly in the simulations that had primordial non-Gaussianity, of using the simulation that has FNL 100. And with that you can see that in here in the plot you have the angular correlation function in blue for the mocks, for the simulations. In orange you have the theory with FNL 100 without using the integral constraint. And if you use now the integral constraint and also you correct your theory with the integral constraint, you have this green line, which essentially tells us that you can recover FNL 100 and you avoid biased results by including this integral constraint. So with that, for the next analysis, we'll be using the integral constraint as a fixed value. The next step was to try to optimize our pipeline for the simulations that resemble the dark energy survey. We have performed some optimization tests in order to obtain the best constraint of FNL as possible. And the main test was trying to test different scale configurations. That is, trying to look for maximum theta angles or different theta binning. And with that, the results are summarized, for example, in this plot, where you can see you have the evolution of the errors in FNL as a function of the theta max values, and also as a function of the theta binning values. Where if you go, for example, to the theta max of 20 and a particular binning of 0.3, you have the smaller error bars for FNL. So with that, we have some prospects. We use MCMC codes to obtain the posterior of the FNL distribution for the almost 2000 mocks. From the maximum of each posterior, we create an histogram, and with this information is essentially summarized in this histogram here. So in here we have selected an optimal configuration. We selected a theta max value of 20 degrees, delta theta of 0.3, and we fix the integral constraint. And with that in here, the results of our work as summarizes in this histogram here or in this table. For example, if we use integral constraint, we have an FNL, really close FNL 0 value, which is what we expect for these simulations. And instead, if we don't use the integral constraint, we will have this -9 value, so a slightly biased value. So this highlights the importance of using the integral constraint. So with that, I'm going to leave you with the conclusions. Essentially, primordial non-Gaussianities will affect the late-time clustering of galaxies via this scale-dependent bias. And with that, we can use that method to constrain this FNL parameter. But this FNL parameter will have a large-scale clustering enhancement, and we need to include this integral constraint in order to avoid biased results. And we also have optimized our pipeline by using these dark energy surface simulations, the ICE Colamox. And we have also some future prospects for maybe the second paper that will include systematic impacts and mitigation and actual application to the real data. So with that, thank you very much to the organizers for the opportunity to give this talk.